Right. Good morning, good afternoon, and welcome to the ARQ Best Practices webinar. This is going to be followed up by a document that will be published in a couple weeks max. The document is ready for going through final approval. So we're going to have a document to go with this. And once the document is published, we will send you a link to it. It will be in the VSF website. Our agenda for today is this. We'll have an introduction by Merrick Ackermans, who's the Director of Transmission for CBS, and the RIST AG Chairman, our main cat wrangler. I will start with the motivation. Then Adi Rosenberg from Alva Links will talk about the sender side, and Sergio Mirata will talk about the receiver side. And then after that, Ruben will show us trying out RIST with the container. So I'll pass on the floor to Rick for his remarks.
Hello. Welcome, everybody. I'd like to welcome everybody here to this session on ARQ best practices. ARQ is the core of RIST in terms of sending packets. It's also used by some other protocols out there besides RIST. And what we are doing is writing up the best methods for using ARQ, hopefully for RIST. I mean, obviously you'd want to use RIST, but also usable for other technologies that use ARQ. Our presentations today are from Sarah Naranya of Cobalt, Adi Rosenberg of Alva Links, Sergio Amarata from SIP Radius, and Ruben Calzadilla from SES. Before we get started, I'd also like to do a bit of a commercial plug. For those of you who are involved in development and may be interested in working on technologies like this and on RIST, that is done by the Video Services Forum, and we are always interested in folks who are interested in helping the development. You do need to be a member of the VSF, which isn't difficult to do. And then we meet every Wednesday at 11 a.m. So if there's anybody out there who's involved in the development of this technology, whether it's products or usage, feel free to join the VSF and to attend our meetings on Wednesdays. We like participation, and the more ideas, the better. So to start it off, I'd like to toss to Ciro Naranya from Cobalt. Take it away, Ciro.
All right, thank you. So what's our motivation in doing this? I want to use the internet for low latency audio video contribution. Stuff like that's been happening forever these days. This is not new using the internet. So I hear that ARQ-based systems such as RIST, which is the best one, are available and mature. It can do a good job. That's true. But, and then there's many buts here. Packet loss on the internet is not uniform and varies over time. So things change. Blocks of packets can be dropped. Dynamic route changes on the internet can cause packets to arrive out of order. So got to deal with that. Packet delivery is also bursty. And there may be a lot of jitter, and then packets can get bunched up. So they come in a burst. Available end-to-end bandwidth varies over time. It may work today and not work tomorrow. Well, you can use multipath to improve reliability, but that also gets complicated. So those are all issues. So what do we do about that? So if you're a vendor or implementer, if you're making that kind of stuff, what features are important for you to have? What controls should you expose? What statistics are important? If you're a user, there may be a lot of configuration parameters. How do I set this thing up? It may be complicated, it may be simple. If I'm looking for products, what advanced features should I be looking for? What are reasonable expectations from an ARQ system over the internet? And how should I monitor this whole thing? So as I say here, the answers are here. And I'm going to toss it to Adi Rosenberg from Links for some of the answers. He's going to talk about the sender side. Take it away, Adi. You got to unmute, Adi.
1 second, I'm trying to find the presentation. 1 second, please. And there we go. And okay, so I'm going to repeat some of what Ciro said about network trouble 101. As this is a repeat of some of the things, I just put enhance on top of that. As Ciro clearly said, regardless if you're using the internet, private, public, cloud networks, they suffer from some of the same issues. Latency fluctuation causing jitter, congestion can cause bursty delivery or slowdown, reordering between packets, back and forth traffic may change over time, meaning that both directions can change. Packet drop can be caused by route changes, rude users that suck all the bandwidth. On-the-way devices can fail and be misconfigured. Hey, let's talk about the outages from the recent cloud providers that were to blame. Oversubscription can come, and of course, poor planning of bandwidth. A reliable delivery system must be able to address these issues head-on. So let's talk about reliable delivery using ARQ. So the first thing we are talking about, the fundamentals is buffer. We need buffer on the receiving end so that latency fluctuation causing jitter, we need to take it out by the use of a buffer. Bursty delivery slowdown, once again, we have a buffer to do that. Any reordering between packets, we need to have a buffer and ordering inside the buffer to take care of that. Back and forth time can change. For that, we need to have a buffer to make sure that whatever communication we send back and forth, we would have enough buffer to deal with that. The packet drops, for that we have the ARQ system. ARQ means that the receiver looks at the packets received and messaging the sender that something has changed, please send a recovery or do something to help me. But that is the ARQ method, regardless if you're using SRT, RIST, ZigZag, or any other technology. That takes care of the routing changes or the root users that basically drop packets. If there is a poor planning of bandwidth, for that we need adaptivity. We need a method to overcome those problems, whether that is that we're changing the source or we are using more paths in order to achieve a better delivery. So what do we need to know about buffer planning? So this is an example of a reliable delivery system. On the left is a sender. On the right is the receiver. And this is not particular for RIST. This is a general method. SRT does exactly the same thing. The sender takes in an original stream, does some control on that, send the data to the receiver. In meantime, put it in a latency buffer so that packets will be ready for any request for retransmissions. On the receiver side, packet gets to a latency buffer that takes care of jitter and any reordering and allows enough time for packets to be recovered or retransmitted. So there is a control method, so then we send indication messages about lost packet reports. Now, why buffer size matters? Because on the receiver end, it does two miraculous functionalities. One, the first section is a reordering time, or as I call it, grace time. That grace time gives you enough time for wait for the packets to arrive. The second one, which as I wrote, grace time, it's a grace time for packets to arrive or to be retransmitted on time to recover any losses that we might have. That buffer on the receiver side basically adds latency. So when you're doing planning, you need to basically understand what are the expectations of your application whether you want to be at a very assured delivery, meaning that I want to recover all the packets, any jitter, or it has to be low latency. That means lower latency buffer, and I need to put more buffer inside. On the sender side, the buffer needs to be, it doesn't add any latency. You can see that in the diagram, but it does need to be somewhat bigger than the receiver buffer so that any request of packet being lost can be received and be sent to the receiver. So let's talk about buffer versus latency. If the receiver buffer is too small, the system will perform badly in poor conditions, like bad quality links, meaning that there is a less chance to send retransmission packets. If you send one retransmission packet and it is lost, then another one will be needed, but you need to have enough buffering to recover that. But if you have a small latency or a small buffer, it will basically not arrive on time. If the receiver buffer is too large, that means it has excessive latency and it won't fit if you have a time-sensitive application. So you need to balance that. The sender buffer, as I showed before, only stores packets for fulfilling a request, so it doesn't have any latency. The latency, however, is in the system is basically governed by the latency of the receiver. It's usually a multiplication, a factor of the number of RTTs, which is round trip time, multiplied by the number of ARQ, retransmission requests that you want to do. So here's an illustration for that. This one is using RIST. SRT has a much more faster recovery request method. So here's the diagram. So first of all, let's understand what is an RTT. RTT is the time for the receiver, for the sender to send a packet between the sender to the receiver, and a message to go back from the receiver to the sender. That is the time. It's a back and forth time. And that time can change between systems. It can change over time. It can change during the course of a day, a week, and a month. So here's an example of how it works. So we start with this packet that being sent to the receiver. We then allow it a grace time, whether it is received or not, and we give it a time for it to appear. If it's not, a receiver will send a request message. Usually it will take half an RTT to reach the sender. It will gracefully send the packet back. You can see it here. It also will take usually half an RTT to reach the receiver. If that packet is lost during transmission, a new ARQ will be sent using the same mechanism, and another packet will be received. Let's assume that it is also dropped. So the third one will be sent, and so on. So this is why the latency buffer is a factor of the RTT that we want to use. And let's see some recommendations afterwards. So what we want to make sure, first of all, the buffer needs to be used for jitter removal from the transmitted data stream. So that we decouple the network behavior from the output of the receiver. So the packets can be outputted using the original transmission rate in the original order that they were sent over the network. The buffer should be able to observe any packet burst and decline packet or any decline in packet reception. Reorder the data packets in the original order and remove any network reordering, detect missing packets, and use ARQ messaging to request the sender to transmit lost packets. And as I said, this is exactly the same for SRT, ZigZee, and other methods out there. The receiver buffer includes these logical sections. A reordering section used to give a grace time for the original packet or retransmitted packet to be declared missing, meaning that that's a small portion of time that we say, let's allow the packet to arrive to the buffer. Maybe there is a latency, maybe something else. let's not just jump the gun too soon. Jumping the gun too soon can create excessive requests and excessive data to be put on the link, and we don't want to do that. A receiver should not send a packet retransmission request at least until the reorder section timeout expires. Then the second phase is the retransmission reassembly section. Usually it is used to receive the original packets and retransmission packets, put retransmission packet instead of any lost packet that may be missing, and allow the system to play it out as needed to the receiver on the other end, which might be a decoder or another system that is waiting for the IP packet to arrive. In the document, we created two types of applications or use cases. One is the low latency live operation parameters. Another one is assured delivery. I'm not going to go over those two tables right now, but you can see on the left is that these are time-critical application, and what we basically want to say is that you need to lower the number of retransmissions, and by that lower the latency buffer of the receiver. On the other end, on the assured delivery, you want to increase the retransmission as much as possible to make sure that you are able to overcome any trouble on the network. Now, let's talk about dealing with packet loss and bandwidth and glitch-free delivery. So first of all, RTT planning. Most delivery systems, just like SRT, ZigZag, and RIST, they have a method to measure the RTT. They are doing that with echo messaging. Packet being sent from the receiver to the sender and then back, so we can measure the RTT. This is being done every second or every several times during a second to get the most accurate RTT out there. That is a dynamic RTT measurement. And from that, a receiver can basically deduce how fast should it request packets, or sometimes what is the network behavior. But sometimes it can cause aggressive behavior, and we suggest for the users and implementers to allow RTT boundaries. This is basically a manual override of the RTT measurement. It is important because sometimes you want to say, hey, I understand that you are doing measurements, but I am smarter than you. I'm a human. I don't want to aggravate. I know the network might sometimes better than you, and I want to put your boundaries. So instead of creating like multiple requests, I will spread out the requests by setting out a manual RTT, so the receiver will be enforced to use the manual RTT to request the packet at a lower rate, and by that, not creating bursts of retransmissions. Now, preparation is key for continuous operation. One way of preparation is to use a multipath communication that can generally improve reliability of an ARQ link and reduce failure. For example, the use of redundant links using SMPTE 2022-7 seamless switching for highest reliability. Use distinct IP and ISPs for each link, meaning that if one ISP link goes down, the other one can survive and continue. If one of the links is glitchy, packets can be recovered from the other link. It's as if you're doing full-time retransmissions, you can recover packets faster than before. You can configure the reordering section, that grace time, to be less equivalent to the latency, to be at least equivalent to the latency between the different paths, so that you can basically wait and take the packets as they arrive. And if one is missing one end, you can recover that from the other end. Only retransmit packets which are lost on both links. If a packet is lost on one link, you can use the packet that arrives on the other link to recover that. Some methods use recovery on both links, and that just aggravates the network, and we say that you should avoid that. If you are using bonding, meaning separating the traffic over multiple links. Reliability can be improved by dynamic load share, which is one of the characteristics and capabilities of RIST. And here's an example. If we are using multipath, use two different distinct paths and service providers. In this example, we send 2 copies, 100% on ISP-A, 100% on ISP-P, meaning that 200% will reach the receiver, but that will give you more reliability. It can overcome ISP failure, packet loss, and you can lower the latency for your application. If you don't care about latency, but you are aware and want to be aware of network performance, you can use dynamic load share. In this example, we use 3 ISPs, and we spread the load between them statically. We start, hey, let's do 45, 45, 10 on this, so there will be 100%. If the packet loss on the link, we can recover some of the packet loss on the same link or other links as we see fit. This is a capability in RIST that most other ARQ methods do not use, Advanced options. These are some of the characteristics that are available in RIST and in, I would say, which protocols do include that. For example, null packet deletion, which is an input which is available, basically removal of null packets. MPEG-2 transport allows to remove null packets, which are stuffing packets. That can give you a saving of between 5 to 15% in bandwidth, which means that you will put 5 to 15% more data packets on the link, which will lower the probability of a packet loss. This is, of course, available in RIST, but from my experience, it's also available with ZigZee, for example, and other proprietary ARQ methods. Something that we added just recently is like it goes the ability to drop low priority PIDs or services, MPEG-2 transport PIDs or services, if the available network bandwidth is exceeded. We can now take unimportant PIDs that are not necessary or services that we deem not important at the moment, so that the entire feed will suffer. We can remove some of the services for the time being, overcoming any fluctuation of bandwidth or decrease of bandwidth, and reinsert them back after condition pickup. So basically, what we do, we take those services or PIDs, we nullify them, convert them to null packet deletion, and the specification for that are in TR06 Part 6. So best practices for sender and advanced options. So this is a model of a sender. So first order of business is, let's put a buffer. We recommend to put a FIFO to receive the messages from the receiver and sort them by the oldest sequence number first. Oldest sequence number first, meaning that it's the sequence number that the receiver is closer to being played out. If we sort that, we will make sure that they will be taken care of first and not any message. That means it gets more priority. Then we say if the receiver works aggressively and sends too many requests for the same packet, we want to only send one packet and not all the requests, so that we will limit the burstiness of the recovery. Next, we introduced and recommend to use rate limit for the retransmission, something which is available also with SRT and ZigZee. And basically, we are pacing the retransmissions packets not to exceed user-defined limits. That will avoid ARQ storms or packets being sent and burst to the receiver, because most networks don't like bursty behavior. Third recommendation is to use bandwidth limit for the whole transmission, meaning the original data and the retransmitted packets, so that we will not exceed the available bandwidth of the link assigned to us. Any violation of the bandwidth will cause packet loss. We basically now impose a limit for ourselves so that we will not go over that limit, and any packet being lost, we can recover that by ourselves. So that makes the sender much more intuitive and more understanding of what is going on and not creating pressure on the network and on the receiver. Also, this is sorry, this is the wrong. When you told me that slide. Next is use source adaptation. So this is the basic mode of the sender on the right. On the left, we see that service selection. We basically take the original stream, we remove services or PIDs that the receiver doesn't want us to send, nullify them, and send them so that the data bandwidth is reduced to overcome any network condition that might be there. And this is the end of my presentation. Thank you.
Thank you, Adi. Was very clear. Now we have Sergio Mirata focusing on the receiver. There's a question here about RIST ARQ with LEO satellites. We'll defer that to the end, and then we'll talk about that. Go ahead, Sergio.
All right. I'm going to be talking about the receiver optimizations, and I'm going to also get into some of the specifics of the Libris implementation of these types of optimizations. Let me start with. All right. So let's go over what we need to do on the receiver side to obtain a high quality, low latency connection that will not kill your network when a major network disruption occurs, which is it's a key element, right? When everything works fine, all the ARQ models out there behave perfectly. What happens when the network misbehaves? When there are bursts of packet loss, when there are, the implementation actually matters in that case, and that's what is going to kill the process. So best use of ARQ demands buffers in both sender and receivers, like we saw with ARI. Getting this right is critical to tuning performance, right? Simply and obviously, if the receiver is too small, it will have less capacity to correct errors and thus be susceptible to the disruption on noisy circuits. But making the buffer too big adds latency. We've seen that the receiver side buffer is the one that controls the latency. And if it's too big, if it defeats the purposes of using RIST and ARQ in general. So let's move to the actual best practices. RTT, like Ari mentioned, the buffer size, first recommendation is, the buffer size be a multiple of the RTT value. And the reasoning for this is clear, right? When a receiver detects a hole in the stream, it will request a retransmission. That request will take a length of time to reach the sender, and then the reply, meaning the missing packet, will be resent and will also take a length of time to reach the receiver again. That combined round trip time will be about 1 RTT worth, right? Because we already measured that, like Ari said, we can measure that 10 times a second is what we do in the Libris library to determine in real time what the RTT is. Under ideal near perfect conditions, we would need to have a buffer of a little bit more than 1 RTT, right? That would allow for the recovery, one-time recovery of any data being missed. However, in reality, when there is packet loss, statistically speaking, the ARQ request itself and the response can both also be lost in transit. So having a buffer that is several multiples of the RTT will allow for subsequent requests of the same missing data, which in turn means that we can recover from higher overall percentages of packet loss. So RTT is very important to have a quality measurement. You can look at our implementation like LibRIST. We do it 10 times a second. And you can actually make your buffer dynamic and be proportional to that measurement. Next. Retransmission requests, when the protocol is properly written, will be self-regulating given the size of the buffer. Like we saw, the document that we're going to publish allows for an optional cap on the bandwidth made available. Ari covered that on the sender side. But in the case of a retransmission request, the receiver can add an optional maximum count on the requests for those packets. These two, when combined, are designed to prevent cascade failure and saturation of your link. If you data is lost and you haven't received it after 3, 4, 5 retries, you can put a max that says, I'm not going to continue looking for this data. Now, how do we make each and every one of these retransmission counts? Well, number one, the receiver should space the retransmission requests to avoid overwhelming the sender and the network. The recommendation that we give is for a gap of slightly more than the RTT between requests. That should be the spacing, right? This allows for enough time for the ARQ request to reach the sender and for the sender to send the reply back. And then we can ask again after a small period of time if we still don't have it. Now, wait before request. If a packet loss is detected, the receiver should wait a reasonable amount of time before considering that packet lost. The time should be somewhere between the reorder buffer size that Ari mentioned and half the RTT time. So that if a packet is coming in out of order or perhaps in a network that has a lot of jitter, we give it time to arrive and we don't consider it lost. The transport medium, whatever it is, the internet or a private network with bad switches or routers, will introduce jitter. And we do not want to send an ARQ request for a packet that could already be in transit. Equally, if the loss of a packet is detected less than 1 RTT before it is due to be used, it is obvious that there's no point in requesting a replacement that is unlikely to arrive in time. You get the packets and you will have to throw them away because you already released the data to whoever was waiting for it. Manage the request list. The receiver must maintain an ordered list of lost packets and the times at which retransmission was last requested. This allows the receiver to remove from the list any request that has timed out because the frame containing the missing packet has already been shown or delivered. In other words, the list should have expiration dates on these missing messages so that you know when they can be taken out. You know that you're not supposed to retransmit them again or add them to the list. It adds a layer of security so that you don't duplicate requests. Final recommendation is that care is taken in defining the size of the reorder buffer on the receiver. The reorder buffer, if it's too small, will result in duplicate packets being received, which adds overhead to the transmission circuit. And that, of course, adds complexity to the receiver error correction. Why duplicates? Because if it's too small, you're going to consider a packet loss and it was actually out of order or it was, arrived late. The suggestion is that the inter-packet arrival time, IAT, be used to dynamically size the buffer, the reorder buffer. The maximum IAT measured over a particular interval, let's say 1 second at a time, should be the lower limit of the size of the reorder buffer. For an implementation that does it, you can look at LibRIST. We measure both the RTT 10 times a second. We measure the inter-packet arrival time based on all the data coming in. And on the inter-packet arrival time, we keep the min, max, and the average. And we use those to dynamically change the reorder buffer to the optimal value. The library also has automatic sizing of the total overall buffer, the rest of the buffer, and it does that based on the RTT measurement. You can put a multiplier and say, I want my buffer to be 3 times, 5 times, whatever it is that you want RTT, and it will keep it at that level. In the case of a dynamic buffer, you of course have to be aware that not all the receivers know how to adapt to a changing buffer. But for those that do, it's a way to have everything dynamic. You don't have to keep an eye or monitor the link. It will auto adjust for you. And I will keep this slide as a reference for any questions that come. Just describes the process of the buffers and the retransmissions, etc. Thank you.
Thank you, Sergio. That diagram you see is going to be in the best practices document that you'll see. So if you can please stop sharing, we'll pass the floor to Ruben. And then after that, we'll have a discussion and we'll get to the questions that showed up. Go ahead, Ruben.
Yeah, well, I mean, I think that there's probably a question out there saying, well, this is great, how we test this. So I'm here to tell you that we have a wrapper that we created around LibRIST and that allows you to do this testing. So we're looking at it right now. So this one is here at home, and I have another one in AWS, and we're going to create a link. But before we get to that, I'm going to show you what is available on the settings. So you have the ability to brand your deployments. So here I have Zip Radius logo, but you can have whatever you want, and you can tweak it to the position in the screen and the size that you want. You can also create a test stream, because sometimes, like this one, for instance, in AWS, I don't have the ability to have a video. So that ability to create that is built in. And you have access control. So if I enable access control, because putting this on the internet, it may require you to control who can access that. You have the ability to actually have only username and passwords, or enable multi-factor authentication. In that case, you will use your authenticator app. The application will give you a QR code that you can scan in order to do that. There is also APIs. So there's multiple documents that we publish with all the APIs. So you can integrate this into something different. And you're going to see an integration that we did with our another application that we're building. And you have some tools, because you may want to check that RTT time. So you have PIN on here. You have also NTR. Thank you, Adi. And then, you can add. And you can actually add the interface that you want that to go out on. So because I'm on AWS and I didn't configure any other interface, it's just showing one here. And you have system logs that you can download. So system logs are logs that whoever interact with the system, deletes something or creates something, is all logging in here. So now let's try to build a flow, a stream, as I call them. And I'm going to go to the system that I have here at home. And the idea is that I'm going to create something that goes from AWS. So the AWS is going to be the sender, and the receiver end is going to be at home here. But since I have my cable router, obviously AWS is not going to be able to reach. So I need to use main profile in order for me to be able to call the sender, and for the sender to initiate, for the receiver to initiate the connection, and then the sender will start flowing. But I will use something that we've been working on, which is an AI orchestrator. And I'm going to give a prompt that says, because now you're going to have your reliable test streams and self-supervise at one point. So I'm going to say, please create a receiver on this machine, which is the machine that are at home, using name RX1. It will be a main profile with a caller role to the sender on 316, which is that was the machine in AWS, using port 12004. The output will be a loopback address. as a placeholder on port 5500 because I don't want to output any multicast from this machine. Enable watch receiver stream. Let's use a buffer of 2000 milliseconds and also create a sender itself. So create everything for me. I don't have an input stream, therefore set a test stream as input. And if the test stream is not enabled, enable it with the scrolling text that says RIST AI orchestrated. I would also like to protect the stream by using a 256 bits key and a secret equals to RIST foreign. And I'm going to send that to the GPU I have at home here. And I come back and says, the human needs to basically check that that everything is okay. And then I'm going to say confirm. And hopefully everything gets orchestrated for me. And once that's done, we're going to go to each of those. Yeah, here you go, connected. All right, so I'm going to start with the sender in AWS, which is here. So it creates a card on the sender that has all the description of what you're doing. This is a TX1, that's the name we gave them. Main profile, this is a TX, this is a transmitter, and you have the ability to see if it's connected or not, the payload, and RIST is up, meaning that the RIST connection is established. You have the RTTs, and if I go here, sorry, you will see that it's using the main profile. There are 4 blocks that you need to configure. In this case, since this main profile has an optional block, and you were basically generating a test stream, you can take a look at the test stream here. You can see that it's actually saying RIST AI orchestrator as we directed. It's listening on port 12004, meaning that it's waiting for the receiver to reach out and establish and initiate the connection. It's using the buffer 2000 as we told them. And also the secret is a RIST foreign with a key size of 256. The one thing I didn't enable is the null packet deletion, but I'm going to do that right now because I want to show that as well. So let's enable that and then save. And then connect again. And here you go. So I'm going to go now to the receiver side to see what's going on in there. So one thing that we notice as we come here is that we see a badge that says service recovered. So something happened, and that is because I disrupted the sender. So the receiver is saying, hey, something happened here. Just check me out. And when we come here, basically, I'm going to go through the same thing. So it's reaching out to that port, is creating the output as a loopback, as I told him, is enabling the receiving watch. So we can actually watch what is coming in. So you can watch exactly what you're receiving. And if I go to the dashboard, I will see that you have the service is being recovered, something happened, and you have the ability to acknowledge that. We're going to acknowledge that for now, but the dashboard will give you all these counters that you can actually reset at any given time, and different windows that you can see the graph. The one thing I'm going to point out here is how there is about 1 meg of distance between what we have before and with null packet deletion enabled. That means that it's about 10%, which is right on what Adit was saying, between 5 and 15. But you have other graphs such as RTT, retransmissions, load, recover, and we're pulling all this from LibRIST. I mean, there's nothing here. It's also the configuration is declarative, meaning that if something happens, this shutdowns, and when it comes back again, it will check what's supposed to be configured, and if this link's supposed to be configured, it will configure it back again. And I think that's all.
Thank you, Ruben. Are you making this available as open source to everybody?
Yes. So
can you post in the chat the link?
Yes, I will post in the chat. So it's right now available on Docker Hub. only. The stable release is 104. And Dr. Sergio Amirata is, we're working with him to find a home, hopefully on the LibRIST video LAN repository as well. Yeah, and I'm going to post the link of the Docker Hub.
Okay, so if you guys want to play with that, it's available. Thank you for doing this, Ruben. So let's get to the discussion part. And the first question is one from here, the audience. Would you talk to the challenges and best practices of using RIST ARQ exclusively with LEO satellite and assume a 10 megabit per second and PEG-4 stream? Who wants that question?
Let me take that one.
Go ahead, Rick.
Okay. The problem with using the reason okay. If you're using it for just general transport, the low latency helps. And I bring that up, though, because I keep having people, including in another meeting last night, asking me about using it for RIST hybrid, which is not necessarily the topic of this meeting. And I keep pointing out that all the LEOs use Ka band. So if you're worried about using this for something like for RIST hybrid, Ka band will fade in the rain quicker than Ku. So obviously I'm focusing on that subsection of it. Others, but for just regular RIST usage, keeping in mind it'll only work in good weather. Well, it won't work in extreme rain. ARQ should work fine for it. But it does have much higher latency, though, than terrestrial. And other folks who want to add on can add on top of that.
Yes.
I'm going to add also that when you're using it just for transmissions, without worrying about rain fade, if you want to use it as your main single link, the 10 megabits per second works fine. You just have to make sure you put a large enough buffer because the gaps can be pretty big on the LEO when it switches. Not any, depending on your region, when it switches from one satellite to another, you can have a gap of a fraction of a second where no data flows through.
Thank you. You want to add something, Eddie?
Yeah, basically I wanted to say what Sergio said. So this is the way you can use the hybrid, basically not a hybrid approach, but you can use a network stream to recap all those 1 second interruption in the LEO, the switchover of LEOs between birds. Should you have a network connection as a backup only for retransmissions, for instance, so you don't pay for that too much, that can recover those LEO mishaps or rain fade. So you have, this is the load share basically. LEO is carrying the bulk of the delivery, the 10 megabits, use an internet connection, set it only to carry only the recovery or a portion of the stream. So then you can recover any mishap on the LEO and you have an assured delivery based on the delay and the latency of the LEO delivery multiplied by the buffer needed in the receiver.
Okay, thanks. There was a comment here that Eutelsat was bonding their LEO with 5G. Okay.
That should work, yeah. Definitely.
Now I'm gonna give you a basic question.
Okay, sure.
You just bought this nice RIST system and you're going to deploy it.
Mm-hmm.
So commissioning, I got it, I'm going to deploy it. You've done that many times. So walk us through too many, yeah. You got a lot of arrows in your back on that. So walk us through the steps you take when you get a new RIST system or ARQ system in general, you're deploying it. What do you do?
Yeah, this is a general for any ARQ system, not specific for RIST. It's applicable for SRT-ZigZag. First of all, trust and verify. You need to trust and check the network. What is your target latency? You need to check the latency between your source to the destination or destinations. You need to test it with a tool. You can use, for instance, MTR, like Ruben mentioned in his tool. He has pings, but better to use that with MTR. So you can see what is the latency and then path behavior between source and destination. What you want to have is something which is rock solid, not fluctuating, not dynamic. If you see that it is dynamic, meaning that changes paths, the MTR basically tells you, hey, the path changes every few minutes, then you need to take care of that. By the way, this is something normal with cloud. So you need to be prepared for that in your buffering on the receiving end. Otherwise, you strive to one latency, you get something else. Do jitter measurements. Don't trust the MTR jitter measurements. You can deploy RIST with a test stream, just like Ruben just showed us. Look for the RTT, look for jitter, the IAT that the Libris, for instance, gives you, or SRT also gives you. Or use something like an iPerf, which is a free tool, which can give you those results as well. With iPerf, you can also check the capability, the bandwidth utilization that you can use. Let's say you want to run 10 megabits, check that you have truly a 10 megabit capable link. I would recommend having at least 20% overhead, or maybe even 30. So if you want to make sure that it is there, test for 13 megabits from sender to receiver to see with a tool like an iPerf. I'm not going to recommend using my own solution in this, but we have a tool that basically does all of that for you. Verified what is going on, so you can test and be sure what is going on. And only once you have all, one thing that I forgot, don't do that for like 10 seconds. Allow it at least 48 hours, and better yet, a week if possible, just to see the fluctuation over time. Sometimes you test something at 10 a.m. and you're going to be live at 6 p.m. Don't trust the 10 a.m. test. You need to test it beforehand when it's going on. So longer duration of test will yield better resilience and preparation when you send a receiver, whether it's RIST, SRT, ZigZag, and so on. That's my recommendation.
Thank you. Sergio, you want to add anything?
Yeah, the way to measure obviously is critical, right? And do not rely on a command line desktop ping, because it's not even using the correct protocol. A lot of people say, oh, look, why is my ping showing this and you're showing something else?
Never trust ping.
It's IGMP is not UDP, is not TCP. It's measure with something that gives you a UDP ping between the two sites.
Okay. So I also hear that if you want full reliability, you need multipath. So same question for either one of you. How do you bring up a multipath system?
Well, I want to mention one anecdote on multipath and cellular bonding, or cellular in general. I found out through another member of the forum that the cellular companies have these algorithms that they're counterintuitive, right? When you have your phone and you don't use data, you would think the minute you need it, it's there. Well, actually, it's not. They have a queuing priority system, and the people that have the data already have the highest priority. So don't wait until you need the data on the cellular connection to actually request it. You have to actually open the channel and keep it open with high bandwidth, and then replace that bandwidth with the stuff that you want, or have it incremental. It's counterintuitive, but it's relevant for this. If you have a regular cellular connection as a backup route and you suddenly need to burst traffic through it, expect a delay of many seconds before you have a high bandwidth available to your account.
Okay, thank you for that. You want to add anything, Adi?
Yeah, basically, as Sergio said, if you're using 4G, 5G, keep it warm somehow. Don't wait for it to someone ramp up the bandwidth for you. There's a lot of resource allocation being carried out, and you are the resource. If you are not using the resource, then it will take time for the cellular system to respond. Usually in multipath, it starts with testing, just like SMPTE 2022-7. You need to test each path individually, see how it is behaving. but then you want to run traffic through both of them. It is very hard to do with standard tools. So for that you need professional tools to run, test the stream, see the how do you want to tune your reception buffer, the latency between the two paths, two or more paths, and then you can decide how do you want to run. Do you want to run 100% of traffic, like full duplication, or may want to use loader, or when you have in RIST, you may want to carry your primary data on the most sturdy path that will carry your bulk, that content, the data, but the recovery can use a lower quality link to carry like a portion or just a recovery. So it will act like a better system and more robust than a standard single link.
Thank you. I think we're about at the end. So, Ruben, do you want to add anything to any of those things?
No, I think I'm good. Thank you, Dr.
All right. Okay, Rick, any final words?
Just once again, anybody who is interested in participating in RIST, feel free to contact the Video Services Forum, sign up, and we meet on Wednesdays. I mean, like I said, the more the better. And I see an Adi hand there.
Yes, Adi.
I do want to, for the audience, one of the things that I noticed over the years that people take an implementation, use default configuration, and hope for the best. And that is bad practice. The reason why we did this presentation and the effort was to basically highlight parameters that are available now with RIST, LibRIST, implementation, SRT, ZigZag, and others that you need to understand, and you need to fine-tune your implementation. Otherwise, default configuration will work 80% of times. If you want it to work 100%, this is where those parameters that we highlighted and the preparation matters. If you don't want to chase your SRT RIST failures, be wary of the network, be wary of the configuration that you need to set so that you will have a peaceful time. You can drink your coffee and not worry about it. That's my recommendation from too many years of working in the field.
Thank you, guys. Again, there is a document coming out from the RIST activity group that has all this in text, and you are going to receive a link to the document once it's officially published. Thank you for attending, and this webinar will also be eventually published. Thank you.
Thank you.